right, so today we're going to look at function operations. So that means like adding functions, multiplying functions, all of the different operations with functions, but then also look into doing composition functions. If you'll recall from Algebra 2, that's kind of like when you did this f of g of x. When you take one function and you're plugging it into the other function. That's called a composite function. Now, you've done this before, but probably primarily algebraically. We're going to look at it also graphically today. One thing we want to do is get familiar with some notation. When you see something like this, where it says f plus g of x, all that really means is that you're going to take f of x, whatever that function is, and you're going to add it to whatever the g function is. Find any like terms, combine them together. You can see it written like this, or you can see it written like this. It means the same thing. Likewise, over here, then that means that you're just taking the f of x and you're subtracting the g of x function. One thing you have to watch out there is that when you're subtracting a function, remember that you have to subtract all of it. There might be multiple terms. You're going to have to distribute that negative. Next one is kind of weird, this fg of x. That just indicates multiplication. There's not a dot there, but there could be. There isn't typically. Just means you're going to take your f function and multiply it by your g function. Might end up doing some FOIL or some distributing, something there. Last one is division. You're just going to take your f function and divide it by your g function. A lot of times, all you're going to be able to do is just write it like that and nothing else happens. Other times, you might be able to simplify. Let's go ahead and try a few of these. I've got our process here. We're going to take f minus g of x. So the f function would be an x squared plus 1. And I'm going to subtract the g function. So it's going to look like this. I'm going to distribute that negative and combine like terms. That's what it will simplify to. And we can just box that in. We're done. Take a look at this next one. It's still f minus g, but instead of x, we're going to do f minus g of negative 3. That just means that you're going to replace your x with a negative 3. I've already done the f minus g of x. I'm just going to take negative 3 and plug it in for all of the x's that we have. I'm going to end up with a negative 3 squared minus 3 times negative 3, and then a minus 4. That's going to turn into 9 plus 9 minus 4. 18 minus 4 is 14. Now that worked pretty nicely, but mostly because I'd already done all the work over here of simplifying them. If this were going to be a process that I had to do over and over multiple times and plugging in different values for x each time, it's going to be worth my time to do what I just did right there. However, to get this answer right here, it didn't just take me this long to do it. I really did all of that and all of this. So don't forget that this really, look at what that really could mean. Ultimately, what I'm doing is I'm putting a negative 3 in to the f function and negative 3 into the g function and then subtracting. That's what this is saying. So I did it right here. Let's check it out. If I do f of negative 3 minus g of negative 3, let's give it a shot. If I put negative 3 into the f function, I'm going to have a negative 3 squared plus 1 minus the whole thing here, plug negative 3 into the g function. So that's going to be 3 times negative 3, and then a plus 5, and I'll have to distribute that negative. That's a 9 plus 1 minus negative 9. That's going to turn into a plus 9, and then minus a 5. And I end up with 10 plus 9 is 19. 19 minus 5 is 14. And looky there, I got the exact same thing regardless of which method I chose. If it's ultimately the rule of thumb is if it's a process that you're going to have to do over and over and over and continue to put different numbers into your functions, it's worth your time to go ahead and clean it up and create a new function. That way you're just plugging it into one thing. If it's a one and done, do this one problem, it's probably quicker just to plug it into each one individually and get your answer and be done. You choose. Let's practice with some multiplication. I've got some functions written up here. My first one says f times g of x. I'm going to take the f function, which is a negative 2x minus 5. I'm going to change colors. Hang on. Negative 2x minus 5. I am multiplying it by the g function, negative 3x. That's just a monomial. I'm just going to distribute it through. I'm going to end up with a positive 6x squared and a positive 15x. My follow-up question is, can you find f times g of 4? And again, I've already gone through the work of doing f times g of x. Why not just plug 4 into this? That'd be a 6, and then I'm going to have a 4 squared plus 15 times 4. That's 6 times 16. 15 times 4 is 60. 6 times 16, golly, that's 96, I hope. All right, getting kind of ugly numbers, kind of large numbers. So I'm going to go with 156 for that answer. Numbers got a little bit big there to be doing mental math, but I pulled it off, I think. Another option could have been just to plug 4 into the f function. That would have been negative 8 minus 5. That would have been a negative 13. Plug 4 into the g function, that's a negative 12. And when you take negative 13 times a negative 12, you'd actually get right back to this 156. Same thing both ways. Last example is to do f divided by g of 0. Since I'm not even finding f divided by g of x, I'm just going to jump right in. I'm going to do f of 0, and I'm going to divide it by g of 0. F of 0, when you plug 0 into x for the f function, you're just going to get a negative 5. And when you plug 0 into the g function, right here, you're just going to get 0, and negative 5 divided by 0 is undefined. That can happen when you're dealing with division of functions. Now, it gets kind of fun when you start dealing with tables and graphs. And what I have here is an f plus g of 4. Now, let's look at this table and make sure you understand what's going on. What this is, it's a pretty common scenario where they're trying to save themselves some space, some time, but this is really two separate tables. It is the f of x table. There's that, where negative 2, negative 3 create an ordered pair, 0, 1 creates an ordered pair, and so forth. But then there's also the g of x function. And we're going to be using the exact same x values. So these are the x values that lead to these y values, or to that g of x. They're just not rewriting the x column. Let me get rid of some of that. If I'm going to do f plus g of 4, I am going to look at it as though it is f of 4 plus g of 4. And then and I got to do it in that order, so I'm going to start here with 4. I'm going to plug it into the f function. When you plug 4 into the f function, you get a 9 back. And then you So I guess I'll go ahead and write that right here. That's a 9. And then you're going to put 4 into your g function. When x is 4, the g function is 2. And 9 plus 2 is 11. Let's try it with multiplication. This notation just means you're taking f of 1 and you're multiplying it by g of 1. F of 1 means plug 1 into the x function and see what you get back. Oh, I got a 3. G of 1, again, plugging 1 in, but into the g function, so I got to go over here and find out, oh, it's actually 1. And 3 times 1 is 3. All right, so let's try the same thing, but doing it with a graph rather than a table. F plus g of 2. Again, this just means take f of 2 and add g of 2. But you're looking at a graph. 2 remembers the x value. When you look at this, the blue line here is my f of x. The red is my g of x. To find f of 2, I plug 2 in for the x value, and I track it up to see what is the y value for the f function, and the y value is a 5. F of 2 is just equal to 5. That is an ugly 5. Let's redo that. Plus, let's do the same thing with your g function. You're going to plug 2 in for x and see what the y value is coming back on that. And I don't know exactly what that is, but I could estimate it. Let's just call it 1.5 for now. If that's a 1.5, then f of 2 plus g of 2 would be 6.5. Same deal. What about fg of 4? Remember, that just means multiplication. Looks weird, so I'd like to throw that one at us every once in a while. Plug 4 into the f function. Track this over here to where x is 4, and then you go up, and it hits the y at 9. F of 4 is 9 times. Now let's do it with the g function. On the g function, you get a 2. And 9 times 2 is 18. See if you can do the next one, f minus g of 1. All right, we're just plugging 1 into the f function, and you get a 3. Plug 1 into the g function, and you get 1. And 3 minus 1 is 2. Hopefully that's what you got. Now we're going to move on to composite functions. And this is to say something like f is composed with g. There's 2 ways that we can see this happening. This is probably the notation you're familiar with. I like this one better. Ultimately, instead of it being f of x, it's f of g of x. X is being replaced by the g of x in the f function. I like the way that that looks. This is another type of way, and probably as you get into upper level math, it becomes a little bit more common that you see it like this. You still say the same thing. It's f of g of x. You still are going to do the g of x first, and then what you get, you put into the f function. And in both of these cases, it means the same thing. The g of x replaces the x in the f function. Given us some functions here, they should start to look familiar, kind of using the same ones over and over. To do h of f of x, what that means is you're going to do f of x first, and you're going to plug it into the h function. So I'm taking this f of x right here, and I'm putting it in for x in the h function right there. It's going to become 2. And then instead of an x, it's going to be a negative 2x minus 5 squared. Now, by now, you should be using our shortcut at squaring a binomial. If you're still doing FOIL, that's really kind of more Algebra 2 level. We're trying to amp it up here, make college algebra a little bit more challenging. I am going to actually really double down here. I am going to square this binomial and take it times 2 at the same time. To square this binomial, you square the first term. That's going to be a 4x squared. But then it's also going to get multiplied by that 2. I'm going to call that 8x squared. The second term comes from you multiplying these and doubling it. So that's going to become a positive 10x. Doubled is a 20x, but times the 2 is a 40x. Now, I should mention here, you cannot distribute the 2 and then square it. Order of operations, you've got to square it first, then take it times the 2. Last step, let's square this last term. That's a 25 times the 2 is a 50. Let's look at our next one. G of f of x. Now remember, I wrote this other notation, but you do whatever's closest to the x first. I'm going to do f of x, and I'm going to plug it into the g function. F of x into the g function. So one more time, I'm taking this same binomial, and I'm putting it into the x in the g function. Now, instead of g looking like negative 3x, it's going to look like negative 3. And instead of the x, it's going to have this negative 2x minus 5. We're going to distribute and be done. Last one, I want you to try this one on your own. All right, you took the negative 3x, you put it in for x. You're going to have to square it, so that's going to end up being a 9x squared. I'm assuming you've already done it, so I'm just shortcutting here. Final answer would be an 18x squared. Let's keep moving. All right, so each one of these, whether we're doing operations or doing composite, we'll start algebraic with the stuff you know, then we'll look at a table, then we're going to look at a graph. Now, this one is f, and notice the shortcut on how they did it. Here's your x's, here's your x matched with the f function, or your x matched with the g function. I'm going to do g of negative 2 first, and then whatever I get, I'm going to plug that into the f function. G of negative 2. So I come down here when x is negative 2, and I go over to the g function. That's a negative 4. If that's a negative 4, now what I'm going to do is f of negative 4. I go back to my table, and I'm looking for the negative 4. There it is. And then I go over to the f function, and I get 5. So what you get as one answer, you plug in to the next function as your new x value. Notation here, g of f of 2. Doing f of 2, taking that answer, plugging it into g. F of 2, right here, gets me a negative 2. So that's a negative 2. Now I'm going to do a g of negative 2. Back to my table at negative 2. The g function is negative 4. Final answer. Next one's kind of fun. I'm going to do g of 0. I'm going to take, oops, that was not what I wanted. This is what I wanted. I'm going to do g of 0, and whatever I get, I'm going to plug it right back into itself. G of 0. Here we are. There's 0. Go over to the g function. It's a negative 5. Now I'm going to do g of negative 5. I get a 4. Let's try it with a graph. Just using the same graph we had last time, f of g of 4. Start off right here, g of 4. Go over to the value of 4, go into the g function, that's a 2. Now I'm going to do f of 2. Plug 2 into the f function and you get 5 back. Okay, I'm going to have you go ahead and pause the video, see if you can do these next two on your own. I'm going to start by doing f of 1. Over here, when I plug 1 in, I get a 3 back for the f. Now I'm going to do g of 3. Plug 3 in to the g function, and we're back at, well, we said this is 1.5. This has got to be a little bit higher. I don't know, 1.8 maybe would be your answer on that one. Last one, another one of those fun ones, f of 1. I'm going to do f of 1 first, doing this piece first. Plug 1 into the f function, and I get a 3. But then I turn around and I plug that 3 right back into the same function. Over here to 3, go up there, and you're left at a 7. All right, I kind of love this last problem. I feel like this is a classic ACT kind of question because you're reading a lot of graphs and taking information from one graph and putting it into the other, and that's exactly what composite functions do. It says here that the graph on the left shows a swimmer's speed as a function of its time. So as soon as they dive into the water, as time progresses, their speed is increasing. But at some point, they're going to kind of level off on that speed, and they're just trying to keep it status quo the rest of the way. All right, next scenario shows the swimmer's oxygen consumption as a function of speed. As the speed starts to increase, initially not much change here, but as that speed increases, so does the oxygen use. Because they're breathing heavy, they're taking in a lot of oxygen at that point. We'll start off and we're just going to find f of g of 1. Plug 1 into the g function. This is the g function. Plug 1 in and we get 5 back. Now you're going to plug 5 into the f function. Same graph. Oops, sorry. 5. Ooh, 5. Interesting. All right, 5 is right here. And I have to go up, and I think it's going to hit at 0.5. So don't think that everything's going to fall on a grid line. It doesn't. Now, next question. What are the speed and oxygen consumption after 20 seconds? Well, the easy question there is the speed. We have a graph right here. After 20 seconds, the speed is 1.5 meters per second. And now we got to do the same thing for the oxygen consumption. However, the oxygen consumption is not based off of the 20 off of time. The 20 seconds is not down here. However, that's where the composite function comes into play. I'm going to put 20 into this function, and I know that it happens at 1.5. So now I'm going to come over here to 1.5 and go up and see, looks like it's a hair below the 10, so maybe a 9. So the oxygen consumption is going to be 9 liters per minute. Do that. All right, that's what it looks like, a composite function on a graph. You take information, you plug something into one graph, whatever you get back is what you plug into the next graph. Next question, how many seconds have elapsed if the swimmer's oxygen consumption is 20 liters per minute? You don't have options. Oxygen consumption is only here. And they tell us that the oxygen consumption is 20. So we're right here in this line. And the only thing I can find out is to go over here to this red curve and find out the speed. And I'm going to say that the speed is somewhere between 2 and 2.5. So I'm going to say 2.25. But that's not my answer. It's 2.25 meters per second. And the question is, how much time has elapsed? Well, if you get an answer of 2.25 here, then you come over to the other graph and you put in, oh, sorry. Yeah, 2.25 for your speed, which is actually up here. 2.25 is about right there. You kind of ride that across, and it looks like my answer is pretty close to a 40 there. If I were to say 40, it would be 40 seconds, which is what they're looking for. They're looking for how many seconds, what's the time going to be? All right. Hope this helps. Go work on your homework.